Welcome to a unique space where we collectively dive deep into the world of the mind and frontier science. This is a sanctuary for the curious, a place where we explore the mysteries, the fascinating truths, and the latest research that shape our understanding of the universe, both the one inside our heads and the one we share. We look beyond the surface, seeking the scientific facts behind the phenomena we often take for granted. Every episode is dedicated to an exploration, guiding you through the layers of complexity to uncover how health, intellect, and the very balance of life are intricately tied to scientific understanding. Tonight, we turn our gaze upwards, towards the star that sustains all life on Earth, yet holds a power we are only beginning to fully appreciate. We are talking about the sun, but not in the way you might expect. Forget the familiar warmth of solar rays or the basic lessons on UV exposure. Tonight, we're going to step past the visible light and delve into the invisible, high-energy threats constantly emanating from our nearest star, threats that impact our technology, our climate, and potentially our biological health in ways that are far more immediate and complex than we previously thought. The central theme for this journey is clear. The sun is more dangerous than we thought. We'll explore the science of coronal mass ejections, are silent, powerful streams of highly energized particles that can and have knocked out global power grids. We will discuss the quiet but constant erosion of our planet's magnetic shield and how it leaves us vulnerable to solar wind. And we'll look at the cutting-edge research suggesting the subtle, cumulative effects of this cosmic radiation on everything from our DNA to the delicate balance of our global communication systems. This is where curiosity meets caution. Prepare to have your perspective shifted on the greatest source of energy in our solar system. Let this conversation guide your focus as we unpack the crucial layers of physics and geology that stand between us and potential solar catastrophe. Now, take a slow, steady breath, find a comfortable position, and let's begin the scientific journey into the extraordinary power of our Sunday. The sun, the source of light and life, is also a profoundly dynamic, turbulent machine, and to truly marvel at its power, we must look beyond its bright, seemingly calm face. We are going to gently begin our exploration with the outermost layer of its atmosphere, a region called the corona. Think of it like approaching an unfamiliar, beautiful fruit. You start with the outer skin before you taste the interior. The corona is that shimmering outer layer, and it is the starting point for some of the most dramatic events in the solar system. To see this region, we need specialized tools because the corona is often swallowed by the sun's blinding photosphere. Instruments like the Solar Dynamics Observatory, launched by NASA in February 2010, were designed precisely for this purpose. The SDO's mission is to seamlessly observe the entire sun, helping us understand the subtle and sometimes terrifying variations that influence our planet and the technology we rely on. It achieves this by observing light far beyond the visible range. We can't just rely on our eyes. We must use the sophisticated tools of physics to make the invisible visible, giving us a continuous, panoramic view of solar weather. When we look at the corona through the SDO's eye, specifically at the 19.3 nanometer wavelength, which corresponds to extreme ultraviolet light, we see a landscape dominated by plasma heated to roughly 1 million Kelvin. This is a quiet kind of magic plasma at temperatures far exceeding the sun's visible surface, yet it's the most diffuse part of its atmosphere. rarely visible to the naked eye, only during a total solar eclipse when the photosphere is blocked. The SDO allows us to study its immense, hidden detail every moment. It's a continuous, uninterrupted stream of data, allowing scientists to map the flow of magnetic energy, tracing the loops and open paths that dictate the sun's activity. This constant monitoring is key to space weather forecasting, as the subtle changes we observe here are often the precursors to major events. It reveals the profound paradox of extreme heat existing in an almost perfect vacuum, where the density is so low that, despite the millions of degrees, an astronaut placed there would freeze. The corona is not static. It is the stage for colossal, high-energy events that define the sun's danger. We must distinguish between two of the most powerful: solar flares and coronal mass ejections, CMEs. When we observe a solar flare, we are looking at plasma heated up to 20 million Kelvin. They appear as intensely vivid, blindingly bright spots, colossal explosions that erupt from the solar surface. The process is one of immense violence. It's a rapid release of electromagnetic radiation caused by the sudden crossing, distortion, and reorganization of powerful magnetic fields threaded through the sun's turbulent plasma. We are talking about events that unleash energy on the scale of millions of nuclear weapons. This immense flash of X-rays and ultraviolet light travels at the speed of light, reaching Earth in just over 8 minutes, potentially disrupting radio communications and GPS signals on the sunlit side of our planet almost instantly. The initial warning, the blinding flash, is instantaneous, but the physical mass is what takes the slower, more menacing journey. However, the real cosmic punch comes from coronal mass ejections, or CMEs. While flares are bursts of light and radiation, CMEs are gargantuan expulsions of matter. They send millions of tons of charged material, plasma, and magnetic field flying out into space at staggering speeds, often hundreds or even thousands of kilometers per second. If you watch a time lapse of this process, you see a dense magnetic structure form, stretching and snapping, then effortlessly launching a bubble of plasma into the solar system. The difference here is crucial. A flare is the light show. A CME is the massive physical shrapnel. It is this physical mass, this magnetic and highly energized material, that poses the most significant threat to our satellites, our communication systems, and our terrestrial electrical grids if that wave of energy happens to be directed right at us. The true danger of a CME lies in its sustained impact. The sheer volume of material that can compress and penetrate our planetary magnetic shield hours or days after the initial blast of the flare. This is where the sun's power truly becomes a threat to modern civilization. As we drift towards sleep while contemplating the sun, we can marvel at the beautiful paradoxes of its structure. Some areas of the corona appear darker. These are known as coronal holes. These regions indicate cooler, less dense plasma, and they are crucially important because they represent areas where the sun's magnetic field lines are magnetically open. Instead of looping back to the surface, these field lines travel straight outward across the entire solar system, like open highways into space. These open pathways allow particles from the solar wind to escape far more easily and stream across space at a higher velocity than the slower, background solar wind. We should think of the solar wind not as a gentle breeze, but as a constant torrent of plasma emanating from these holes. Coronal holes can persist for weeks or months, ensuring a steady stream of high-speed particles flows toward Earth even when the sun appears relatively calm. When these energized solar wind particles eventually collide with the Earth's magnetosphere, they interact with the gases in our atmosphere, generating the breathtaking beauty of the aurora lights, the northern and southern lights at our polar regions. It's a beautiful, quiet kind of magic at the boundary of our planetary protection, a constant reminder of the unseen energy flowing from our star. It is a visual manifestation of a high-speed collision, a delicate boundary defense system reacting to the unrelenting power of the sun, quietly showing us the influence of solar activity on our night sky. To understand the sun, we must appreciate its breathtaking complexity. Consider the phenomena of solar filaments, or prominences, as they are called when viewed at the edge of the sunday. These are enormous loops of plasma rising from the surface, often stretching for hundreds of thousands of kilometers. Our Earth would be a tiny speck next to one of them. While they can form in a day, stable ones can exist for months, swiftly moved and shaped by intense magnetic fields. This movement is not random. It's a direct consequence of the continuous fight between gravity trying to pull the plasma down and magnetic forces attempting to hold it aloft, a struggle that results in these visually stunning structures. A related, equally fascinating feature is coronal rain plasma that is cooled and is trapped by magnetic fields, eventually falling back to the surface, despite being millions of degrees hot itself. This gentle descent, observed with high-resolution instruments, highlights the constant state of flux and the localized cooling mechanisms at work within the corona's structure. When scientists observe these features, they often use different light filters. For example, the 30-nanometer wavelength, extreme UV, is vital for imaging CMEs and these dynamic loop structures. And the frequency of these structures, their coming and going, is heavily dependent on the 11-year solar cycle, a rhythmic beat of activity we will dive into more deeply later on. This cycle dictates whether the sun is in a period of relative calm or magnetic frenzy, which directly correlates to the number of filaments and flares we observe. The true value of solar observation lies in using dual wavelengths, or even multiple wavelengths simultaneously. By comparing two images of the corona taken at the exact same time but using different filters, we gain profound insight into the thermal landscape. An image tuned to 600,000 Kelvin might clearly depict the quiet, looping structure of the corona, highlighting the magnetic skeleton and cooler plasma flows. However, an image tuned to 2 million Kelvin might only display the much hotter, hyperactive regions where flares and CMEs are brewing, showing us where energy is rapidly being injected. The stark contrast between these two perspectives highlights a profound paradox. Two distinct, vastly different thermal environments existing in the same space, requiring multiple observational approaches to effortlessly reveal their complex, intertwined nature. This is how we begin to decode the physics of heating the corona to such impossible temperatures, a mystery that has puzzled solar physicists for decades. Now, let's turn our attention inward, moving gently past the corona towards the sun's visible face. The first layer we encounter is the transition region, best seen around the 160 nanometer wavelength. It is an incredibly shallow layer, perhaps only 100 kilometers thick, yet this thin boundary hosts one of the most dramatic temperature shifts in the solar system. The temperature rises exponentially from around sim 8,000 Kelvin to a staggering 500,000 Kelvin. To put that in perspective, hot lava on Earth is only about sim 1,443 Kelvin. This massive, sudden thermal leap remains one of the greatest unsolved problems in solar physics. How does the sun manage to suddenly superheat its atmosphere in such a small space? The search for this answer continues to drive major solar research, and every new piece of observational data offers a subtle clue into this furnace of energy transfer. Beneath this turbulent boundary lies the chromosphere, the last atmospheric layer before the surface, visible in 170 nanometer UV light. It's about 1,700 kilometers thick, and its key feature is the mesmerizing presence of spicules. These are long, bright jets of plasma that shoot upward at speeds up to 100 kilometers per second, reaching nearly 10,000 kilometers in length. They form and vanish again quickly, often in just 5 to 10 minutes. Their mechanism was a mystery until 2017, when scientists realized that by adding neutral particles to their magnetic models, the charged plasma particles gain the buoyancy necessary to escape and form these fleeting, beautiful structures. It's a reminder that even the smallest, most rapidly moving features have complex, hidden physics behind them. Finally, we arrive at the photosphere, what we perceive as the sun's surface, best imaged using visible light. We are often taught to think of this as a solid boundary, but it is not. The entire sun is a plasma, the fourth state of matter, making up an estimated 99.9% of the matter in the universe. Plasma behaves like a gas, but is made of ionized atoms and free electrons. The photosphere itself is a relatively shallow layer, about 400 kilometers deep, and it's the deepest layer scientists can measure directly. Here, we observe sunspots. They appear dark because they are cooler than their surroundings, which seems counterintuitive on a star. The cause is incredibly powerful magnetic fields that emerge through the surface. These fields trap heat beneath the photosphere, blocking the convective flow of energy, thus chilling the surface plasma in that region. When we compare visible light images with UV images, we see sunspots and solar flares coincide at the exact same location, creating an effortlessly clear connection between the magnetic activity and the explosive potential. These sunspots can range from 15 kilometers to colossal structures 160,000 kilometers wide, dwarfing our own planet multiple times over, giving us a profound sense of the scale of magnetic power at work and serving as the visual markers for the most dangerous solar events. When we compare visible light images with UV images, we see sunspots and solar flares coincide at the exact same location, creating an effortlessly clear connection between the magnetic activity and the explosive potential. These sunspots can range from 15 kilometers to colossal structures 160,000 kilometers wide, dwarfing our own planet multiple times over, giving us a profound sense of the scale of magnetic power at work and serving as the visual markers for the most dangerous solar events. Now, we must turn our attention inward. Having analyzed the visible surface and atmosphere, we must attempt to peer beneath that bright, churning boundary. While the photosphere seems like a solid, glowing boundary, it is merely the place where the sun's plasma becomes transparent enough for photons to escape. To truly understand the engine that drives those massive magnetic fields, the same fields that produce the most violent solar storms, we must examine the layer directly beneath, the convection zone. This is where the star's heat is physically hauled toward the surface. To get a closer look at this boundary, high-resolution instruments like the Swedish Solar Telescope, an Earth-based telescope that uses visible light around 400 nanometers, offer unparalleled detail. Looking through the SST, we don't just see sunspots, we see the very texture of the surface itself. This texture is the direct visual proof of the underlying energy transfer mechanism, a quiet kind of magic revealing the inner workings of our star. This crucial texture is known as solar granulation. If you look at an image of the sun's surface with enough resolution, you'll notice it isn't smooth. It's covered in jagged-edged, shape-shifting cells. These cells, or granules, resemble the cooling, cracking surface of molten lava, and they are enormous. Each one is typically about 1,000 kilometers wide, roughly the size of a major continent on Earth. This granulation is not noise or a photographic error. It is the physical manifestation of convection currents, the very same basic mechanism that drives plate tectonics within Earth's mantle or causes water to boil in a pot. The mechanism is elegant and relentless. The brighter center of each granule is where unimaginably hot fluid plasma rises from the sun's upper interior, carrying heat upward. This buoyant plasma then spreads outward across the boundary layer, slowly cooling as it goes. The darker boundaries you see are where that cooled fluid sinks back inward, descending to be reheated, thus completing and repeating the cycle. This churning is constant and violent. Each granule is incredibly transient, lasting for as little as 20 minutes before it is replaced by a new one, constantly renewing the surface. The plasma flows within these cells reach supersonic speeds, often exceeding 7 kilometers per second, generating powerful waves and sonic booms that ripple across the surface. This continuous, violent churning is the root cause of the sun's magnetic activity, amplifying and twisting the magnetic field lines. And this graininess we see even in the full disk image from the SDO is this actual granulation, not an image artifact. It is the visible sign of the profound amount of energy being released from the interior. And yet, this is where our direct observational journey ends. The photosphere is the boundary of observation. Below this layer, the plasma is so dense and opaque that photons cannot escape, meaning no telescope, using any spectrum of light, can yet image deeper into the sunday. The interior layers, the radiation zone, and the central core remain a mystery viewed only through theoretical models and indirect measurements like helioseismology. Though the deep interior is shielded from our sight, understanding the sun's birth provides the essential context for its overwhelming power and its potential danger. We must now gently turn to the theoretical journey of how this magnificent, dangerous star was born. Our journey starts not with light, but with darkness, the cosmic nursery where stars are born. This era was approximately 4.6 billion years ago, predating the entire solar system. Our sun began as a tiny, dense pocket within a giant molecular cloud, a massive, cold cloud of gas and dust spanning hundreds of light years across and possessing the mass of millions of suns. Its composition was a cosmic mix of hydrogen, helium, and scattered heavier elements like carbon, oxygen, and iron, the cosmic remnants forged by ancient, long-dead supernovae. For this calm, vast cloud to collapse, it needed a trigger. Scientists hypothesize that the initiation came from a shockwave, perhaps from a nearby supernova, which some hypothetically name Coatlicue. This shock wave acted like a cosmic hammer, compressing parts of the cloud and critically increasing the local density. This dense, collapsed region that was destined to birth our star and planets is known as the Presolar Nebula. Crucially, the cloud didn't collapse into a single body. It fragmented into multiple dense clumps, This collapse mechanism is governed by the Jeans instability, named after Sir James Jeans. Collapse occurs when a section of the cloud exceeds the Jeans length, the threshold where the inward force of gravity definitively overcomes the outward pressure of the internal gas. The moment this instability is met, the collapse becomes both inevitable and incredibly rapid, drawing in mass from the surrounding cloud. The resulting clump enters the protostellar phases. It first becomes a protostellar core, rapidly contracting under gravity, and is surrounded by infalling gas and dust. As the core contracts, it becomes denser and hotter. This heats it into a protostar, which begins to emit light and heat primarily from the immense energy released by gravitational contraction. This is a critical detail. Even at this stage, the core temperature is not yet high enough for the nuclear fusion that defines a star. It is simply converting gravitational potential energy into heat. The process of ignition and stability is the star's true birth. Gravitational contraction continues for millions of years, compressing the core until it reaches the necessary ignition temperature, approximately 10 million degrees Celsius. At this point, the pressure and heat finally become sufficient, and hydrogen nuclei start to fuse into helium. This is the spark, the definitive birth of our Sunday. As the cloud collapsed, its slight initial rotation was amplified due to the conservation of angular momentum, much like a figure skater pulling in their arms to spin faster. This rotation caused the remaining material around the equator of the newly forming star to flatten into a disk, as that material was moving fast enough to orbit rather than fall inward. This flattened, spinning cloud is the protoplanetary disk, the birthplace of all the planets, moons, and asteroids in our solar system. Another example of physics shaping life effortlessly. With fusion ignited, the sun settles into hydrostatic equilibrium, entering the main sequence phase. The vast energy from nuclear fusion creates an immense outward radiation pressure that perfectly balances the relentless inward force of gravity. The star stops contracting and achieves a stable, long-term state. This balance, the defining axis of its existence, will govern every stage of the sun's life for billions of years to come, a profound paradox of opposing forces held in perfect check. This balance is maintained by the nuclear engine within the sun's core, an environment of unimaginable extremes. The temperature is around 15 million degrees Celsius, and the pressure is an astonishing 250 billion times that of Earth's atmosphere. Under these conditions, the hydrogen atoms are stripped of their electrons, forming a plasma of free protons and electrons. Herein lies one of the most profound paradoxes in astrophysics. The core is hot, but not hot enough. Protons, all carrying the same positive electric charge, naturally repel each other. This is the Coulomb barrier, the massive electrostatic repulsion that prevents the protons from getting close enough to stick together. According to classical physics, the sun's core temperature should have been thousands of times higher to provide the kinetic energy needed to overcome or climb over this barrier. Based on classical models, the sun shouldn't be fusing hydrogen at all. The solution to this paradox lies not in classical physics, but in the strange, counterintuitive world of quantum mechanics, the model where particles must be treated as both waves and particles. The key phenomenon is quantum tunneling. In this quantum view, particles have a small, non-zero probability of literally tunneling through the energy barrier, even if they don't possess the classical energy required to pass over it. It is a statistical loophole, a quiet kind of magic. that allows a small fraction of the billions upon billions of protons to bypass the Coulomb barrier, making fusion possible at the sun's operating temperature. Without this quantum effect, there would be no energy, no equilibrium, and therefore no life on Earth. The process that sustains the sun, the nuclear engine driving its existence, is known as the proton-proton P chain, and it accounts for approximately 99% of the star's energy production. This is a graceful, yet complex, multi-step pathway, beginning with a seemingly impossible collision. The first step requires two protons to collide, and for one to effortlessly transform into a neutron via the weak nuclear force. This extremely rare event is absolutely essential, as it combines the two protons into deuterium, a heavy hydrogen isotope, while simultaneously releasing a positron, the anti-electron, and that ghostly, elusive particle known as a neutrino. Once deuterium is formed, it quickly proceeds to the second step, where it collides with another proton to form helium-3, a reaction that instantly releases a high-energy photon known as a gamma ray. The chain culminates in the final step, the key to its immense power. Two of those helium-3 nuclei collide. This interaction results in a stable helium-4 nucleus, releasing two protons back into the system to restart the entire chain. Most importantly, this final fusion unleashes a significant amount of energy in the form of radiation, completing the cycle that creates the outward pressure, maintaining the sun's perfect, delicate, hydrostatic equilibrium for billions of years to come. While the P chain dominates, there is also the CNO cycle, the carbon-nitrogen-oxygen cycle, where carbon, nitrogen, and oxygen nuclei act as catalysts to fuse protons into helium. This cycle is dominant in stars hotter and more massive than the sun, but it still contributes a small percentage to our star's total energy output, quietly reminding us of the diverse processes occurring within stars across the galaxy. The sustained release of energy from these fusion pathways is what creates the outward pressure, completing the perfect circle of hydrostatic equilibrium and ensuring the sun will continue to burn steadily for billions more years until the hydrogen fuel is eventually exhausted. While the P chain dominates, there is also the CNO cycle, the carbon-nitrogen-oxygen cycle, where carbon, nitrogen, and oxygen nuclei act as catalysts to fuse protons into helium. This cycle is dominant in stars hotter and more massive than the sun, but it still contributes a small percentage to our star's total energy output, quietly reminding us of the diverse processes occurring within stars across the galaxy. The sustained release of energy from these fusion pathways is what creates the outward pressure, completing the perfect circle of hydrostatic equilibrium and ensuring the sun will continue to burn steadily for billions more years until the hydrogen fuel is eventually exhausted. The source of the sun's entire power can be traced back to the fundamental principle of mass-energy conversion, famously encapsulated by Einstein's equation, E equals mc2. This process is the ultimate definition of stellar efficiency. Fusion converts a tiny fraction of mass into pure energy. The resulting helium-4 nucleus has slightly less mass than the 4 original protons that went into creating it. The scale of this loss is nearly incomprehensible. The sun converts approximately 4.3 million tons of mass into pure energy every single second. To put that into perspective, that's roughly the equivalent mass of 3 million cars vanishing into light and heat every single tick of the clock. sustained effortlessly for billions of years. This immense loss powers the sun and provides the precise light and heat that makes Earth habitable, a testament to the power locked within atomic bonds. Once this energy is created in the form of high-energy photons, it begins what is arguably one of the most epic and chaotic journeys in the universe: the photon's epic, chaotic journey. A single photon born in the core must navigate and escape roughly 700,000 kilometers of chaotic solar interior. Due to the extreme density and constant interaction, this journey takes an astonishingly long time, from tens of thousands to potentially hundreds of thousands of years before that photon reaches the surface and speeds away. The journey begins in the core, the fusion site itself. Though it only spans about 25% of the sun's radius, this region holds nearly half of the star's total mass. It is incredibly dense, around 160 grams per cubic centimeter, making it over 20 times denser than solid iron here on Earth. This density creates the phenomenon known as the random walk. The environment is so packed that a photon, instead of traveling in a straight line, is almost immediately absorbed by a neighboring particle and then re-emitted in a completely random direction. It's like trying to navigate a densely packed crowd while being perpetually shoved sideways. This erratic, zigzagging movement, which precisely models Brownian motion, the erratic movement of particles due to collisions, means the photon travels an enormous total distance, potentially hundreds of thousands of light years worth of movement before making any net outward progress. With every collision, the photon loses a tiny bit of energy, slowly shifting its identity from a high-energy gamma ray into an X-ray, and eventually into visible light as it works its way outward. Because we cannot directly observe the core, scientists rely on indirect observation methods to pierce this veil of density. Helioseismology is one such technique, the study of vibrations, or sound waves, that constantly ripple across the sun's surface. These waves are precisely measured using the Doppler shift of light from instruments like the SOHO and SDO satellites. Since the wave velocity is fundamentally influenced by the temperature, density, and composition of the layers they pass through, scientists can perform an ultrasound of the sunday by tracking how long it takes sound waves to travel from one side of the sun to another. They can create highly detailed, three-dimensional models of the internal structure, much like seismologists study earthquakes to infer the composition of our own planet's interior. This allows us to map the precise boundary between the convective and radiative zones, adding confidence to our theoretical models. The most direct link to the core is provided by solar neutrinos. These elusive subatomic particles are released during the initial step of hydrogen fusion. Since neutrinos rarely interact with matter, they can pass through a light year of lead without stopping. They travel straight out of the sun, unaffected by the dense interior, reaching Earth in about 2 seconds. For a long time, the measured flux of these particles was only about 1/3 of what models predicted, a critical inconsistency known as the solar neutrino problem. The resolution of this puzzle, a profound paradox in itself, was discovered when scientists confirmed that neutrinos are not massless, but are quantum particles that oscillate. They change flavors or types on their way to Earth. This discovery not only perfectly confirmed our detailed model of fusion in the core, but also validated a new, fundamental aspect of particle physics, proving that the sun's core is working exactly as our equations predicted. After leaving the core, the photon enters the radiative zone. This immense layer extends from the core's edge out to about 70% of the sun's radius. As we move outward, conditions change dramatically. the temperature drops from 15 million to around 2 million degrees Celsius, and the density drops sharply from being denser than gold to less dense than water. The primary method of energy transport here is radiative diffusion, the continued frenetic scattering of photons. As the density drops, photons gain slightly more wiggle room, taking slightly bigger leaps between their constant interactions. However, the solar material remains highly opaque. A few centimeters of plasma in this region blocks as much light as hundreds of meters of water. This prolonged, slow interaction is why the journey takes such a staggering amount of time. To understand this unseen domain, scientists rely on the Standard Solar Model, SSM. This is a robust mathematical framework built upon fundamental principles like hydrostatic equilibrium, energy conservation, and radiative transfer. The SSM's function is to mathematically infer the interior properties, such as temperature, pressure, and density gradients, and model precisely how energy is passed between particles via photon transport. The mathematical power of this model allows for the contemplative exploration of unvisitable environments, bridging the gap between direct observation and theoretical physics with striking accuracy. The boundary between the radiative zone and the next layer is one of the most crucial and mysterious spots on the Sun, the tachocline. This is a thin, transitional layer of shear stress, where the smooth, uniform, solid body rotation of the deep radiative zone meets the boiling, turbulent, differential rotation of the convective zone, where the equator spins faster than the poles. This dramatic contrast in flow here is thought to be the engine for the solar dynamo, the mechanism that twists, amplifies, and tangles the Sun's magnetic field. As the plasma stretches, twists, and coils the field lines, it generates the immense magnetic strength necessary to create sunspots and solar flares. This quiet, deep-seated layer is, therefore, the true source of all the magnetic violence we observe on the surface. Finally, the energy reaches the convective zone, which extends from about 70% of the radius to just beneath the photosphere. Here, the temperature drops to below 2 million degrees Celsius. At this point, the plasma is no longer dense enough for the efficient radiative diffusion seen in the previous layer. The dominant transport method switches entirely to convection, the massive currents we observed earlier. Hot plasma surges upward in massive cells, thousands of kilometers in diameter, due to buoyancy, and cooler plasma sinks, carrying energy toward the surface like boiling water. This process is far more efficient at moving energy than radiative diffusion, surging upward at hundreds of meters per second. The sheer force involved is immense. The kinetic energy released in one of these surges is equivalent to the combined destructive power of 10 billion hurricanes. The photon's long, chaotic journey, a cosmic pinball game lasting millennia, finally ends at the photosphere, the visible surface, and the very top of the convective zone. Here, temperatures cool dramatically to about 5,500 degrees Celsius. The plasma becomes sufficiently thin, the opacity finally drops for the photon to escape the star's relentless grip. This thin, approximately 500 kilometer deep layer is the boundary from which the light we see is finally emitted. After thousands of years of zigzagging through dense solar material, the photon finally breaks free, traveling at the ultimate speed limit of the universe, the speed of light, toward Earth, concluding its long, chaotic transit. When that photon leaves the photosphere, it leaves behind the slow, turbulent world of plasma and begins its 8-minute dash through the vacuum of space. Meanwhile, its ghostly neutrino friend, created at the exact same moment in the core, is likely already long out of the Milky Way galaxy, having experienced none of the sun's interior drama. This disparity in journeys offers a profound paradox in physics. Two particles born simultaneously, one arriving in mere seconds, the other taking thousands of years to deliver the light we depend on. The sun is currently in its stable phase, known as the main sequence, but it is not truly static. A lifelong, subtle trend known as main sequence changes dictates that the sun's brightness has already gradually increased by about 30% over its lifetime. This seemingly innocuous number carries catastrophic weight for our planet's distant future. The underlying cause of this slow, relentless brightening is the inevitable buildup of helium ash in the core. As hydrogen fusion converts protons into helium, this heavier, inert helium accumulates. Since helium requires much higher temperatures than hydrogen to fuse, it acts as a passive contaminant, diluting the hydrogen fuel and reducing the outward radiation pressure that counters gravity. Gravity begins to dominate, causing the helium-rich core to contract and become denser. To prevent complete, catastrophic collapse, the temperature in the shell of hydrogen surrounding the core must be increased. This forces an increase in the rate of hydrogen fusion to restore the crucial hydrostatic equilibrium. This gradual, almost imperceptible cycle of core contraction and hotter fusion is what slowly brightens our star, a silent, slow change that will eventually have devastating consequences for our planet's habitability long before the sun reaches its final, dramatic phase. Scientists estimate that just a 10% increase in solar luminosity from today would trigger a runaway greenhouse effect on Earth, boiling the oceans and making the planet uninhabitable. This slow, steady burn is a quiet kind of magic that contains a future cataclysm. This leads us to the inevitable, ultimate contemplation of the sun's dramatic death, a phase that will begin in about 5 billion years. This event will not be a sudden, violent explosion, but a prolonged, effortless inflation. When the core finally becomes overburdened with inert helium, the thin shell of surrounding hydrogen fusion can no longer sustain the star against the pull of gravity. The sun will dramatically expand, entering the red giant phase. During this transition, the outer layers of the star will balloon outward, potentially swelling to over 200 times its current size, consuming its luminosity and engulfing the inner planets Mercury, Venus, and possibly Earth itself. The intense heat from the expanding shell will vaporize our oceans and atmosphere, rendering our world a dead cinder. Even as the outer layers expand, the core continues to contract and heat. This compression continues until the core reaches a critical temperature of approximately 100 million degrees Celsius. At this point, the helium ignites in a catastrophic runaway event known as a helium flash, starting the fusion of helium into heavier elements like carbon and oxygen through the triple alpha process. The triple alpha process involves 3 helium nuclei, alpha particles, fusing to form one carbon nucleus, releasing immense energy. This sudden ignition provides temporary stability, giving the sun a second life as a slightly smaller, more stable red giant fusing helium in its core. Following this helium burning phase, the star's second life will also end. The sun will swell further before shedding its outer layers into space. These expelled gases will travel outward, ionized by the remaining hot core, forming a beautifully colored but ghostly remnant known as a planetary nebula. This nebula, rich with newly created elements like carbon and oxygen, the building blocks of future life, and rocky planets, will eventually seed new generations of stars and solar systems. The intense colors we observe in distant planetary nebulae are the final, beautiful cosmic exhale of a dying star. The remaining core, once the engine of life, will be left behind as a dense, Earth-sized stellar corpse called a white dwarf. The white dwarf is composed primarily of electron-degenerate matter, a substance so dense that a teaspoon of it would weigh tons. This remnant will slowly cool and fade over trillions of years, becoming a cold, dark, black dwarf. This ultimate cosmic fate gives us a profound sense of time and the temporary nature of even the most powerful stars, reminding us to marvel at the delicate, fleeting stability we experience today, living under a star in its tranquil, life-giving prime. Following this helium-burning phase, the star's second life will also end. The sun will swell further before shedding its outer layers into space. These expelled gases will travel outward, ionized by the remaining hot core, forming a beautifully colored but ghostly remnant known as a planetary nebula. This nebula, rich with newly created elements like carbon and oxygen, the building blocks of future life and rocky planets, will eventually seed new generations of stars and solar systems. The intense colors we observe in distant planetary nebulae are the final, beautiful cosmic exhale of a dying star. The remaining core, once the engine of life, will be left behind as a dense, Earth-sized stellar corpse called a white dwarf. The white dwarf is composed primarily of electron-degenerate matter, a substance so dense that a teaspoon of it would weigh tons. This remnant will slowly cool and fade over trillions of years, becoming a cold, dark, black dwarf. This ultimate cosmic fate gives us a profound sense of time and the temporary nature of even the most powerful stars, reminding us to marvel at the delicate, fleeting stability we experience today, living under a star in its tranquil, life-giving prime. From our vantage point on Earth, the sun presents a profound paradox. It appears to be a source of calm, steady light, a fixed lamp in the sky. Yet when observed with the tools of science, we see it as a turbulent, moving ocean of plasma. Within this churning ocean, magnetic fields constantly knot and unknot themselves. Bright flares flash with the energy of a billion bombs, dark sunspots grow and fade, and massive coronal mass ejections race into space. All this activity is governed by a single, predictable core pattern. Solar activity rises and falls in a repeating magnetic cycle. This is the sun's rhythm, the beat that drives space weather. There are two primary cycles that define this rhythm. The most commonly discussed is the Schwabe cycle, often known as the 11-year cycle. This cycle swings between two extremes: the solar minimum, a quiet phase where weeks can pass with almost no sunspots and very few large bursts of energy. During this time, the solar wind is generally slower and more uniform. Conversely, the solar maximum is the busy phase. Dark sunspots become common, flares are frequent, and the sun can fire off powerful CMEs more than once a day. This is the period when Earth's technology is most at risk. Overlaying the 11-year cycle is the larger Hale cycle, a 22-year cycle. This longer rhythm is purely magnetic. Every two Schwabe cycles, The sun's global magnetic field flips the magnetic north and south poles, swap places, and then swap back again after another 11 years. This magnetic flip is essential, as it's tied to the formation and location of sunspots and directly influences the overall strength and timing of the busiest years. The mystery of the timing is a key area of ongoing research. Why does the cycle last approximately 11 years instead of, say, 5 or 15? We know the cycle is fundamentally magnetic, driven by the movement of conducting plasma and differential rotation within the sunday. One historical hypothesis, now largely dismissed, noted the coincidence of the Sim 11-year cycle with Jupiter's orbit. However, Jupiter's gravitational influence is far too weak to explain the complexity, shifts in strength, or variations in the length of the solar cycle. The truly likely answer lies in the internal hypothesis. The cause is rooted deep within the sun's internal flows and the intense shear near the tachocline, the transitional layer separating the smooth radiative zone from the turbulent convective zone. It is the physics of this deep magnetic layer that sets the fundamental, effortless rhythm of our star. The sun's rhythm dictates space weather, the dynamic changes in the space environment near Earth. The most potent manifestation of this is the geomagnetic storm. These storms are not caused by the sun's light, but by flares and CMEs that send immense streams of charged particles and knots of highly organized magnetic field past Earth. Geomagnetic storms result when this intense solar output rattles Earth's protective magnetic field, causing it to compress and release energy. Fortunately, modern science allows for mitigation. Dedicated space weather centers constantly track the sun and the solar wind, issuing warnings days in advance. This lead time is crucial. It allows astronauts to shelter from radiation and satellite operators to put sensitive systems into safe modes, preventing costly or catastrophic damage. The impacts are most immediate in low Earth orbit. During periods of intense solar activity, radiation and magnetic changes heat the top of the atmosphere, causing the heated air to expand upward. This results in significantly increased atmospheric drag on LEO satellites, requiring more frequent maneuvers to stay aloft. In strong storms, the drag can be so pronounced that it potentially brings satellites down faster than planned, creating a critical risk for operators. On the ground, impacts on communication and infrastructure are widespread. Ionosphere disruption occurs when extra-charged particles in the ionosphere bend and smear radio waves. GPS accuracy can degrade significantly, potentially slipping from accuracy of 1 meter to 10 meters or more. Radio waves, essential for emergency and military communication, can suffer radio blackouts. Conversely, the disturbed ionosphere can allow amateur radio operators to bounce signals over surprisingly longer distances. Crucially, ground infrastructure like long-distance power grids must prepare for extra electrical currents induced in their long wire systems by the fluctuating magnetic field, which can overheat and damage transformers. Furthermore, airlines frequently alter high-latitude routes during storms to avoid elevated radiation levels and communication blackouts. In summary, during solar maximum, our technology is simply a little less steady, a profound paradox given how much we rely on its stability. Yet, there's beauty in the disturbance, the aurora. The aurora lights are the direct result of fast particles traveling down Earth's magnetic field lines and striking the thin air near the poles. During active years, auroras become much more common and creep farther from the poles, allowing people in lower latitudes to witness this spectacular display, the visual poetry written by the solar wind on our atmosphere. Beyond the dramatic impacts on technology, the sun's rhythm exerts more subtle nudges on Earth's environment. The relationship between cosmic rays and cloud seeding is an example of an unsettled theory. When the sun is quiet, the protective solar windshield relaxes, allowing more cosmic rays from the galaxy to reach our atmosphere. When the sun is active, its stronger magnetic field blocks more cosmic rays. The unsettling theory suggests that these cosmic rays may help seed cloud droplets, potentially leading to small shifts in low cloud cover and, therefore, the amount of sunlight reaching the ground. This idea remains under intense study and is not yet settled fact, illustrating the complex, nuanced ways the cosmos might influence our climate. These solar variations also contribute to small climate nudges and biological responses. Added energy in the upper air during active times can slightly alter winds and atmospheric waves, which then move downward, causing modest changes at ground level, typically only about tenths of a degree. While small, this still impacts sensitive natural systems. For instance, studies have linked the egg-laying dates of certain bird species, like blue tits, to sunspot numbers, using sunspot counts as a proxy for solar cues or warmth. More compellingly, magnetism-sensing species are affected. Migratory animals like sea turtles and homing pigeons rely on the Earth's magnetic field for navigation, and they may need to adjust their routes or timing when the field is disturbed by a geomagnetic storm. It is a quiet kind of magic how these massive cosmic forces can influence the minute biological clocks of Earth's creatures. The effects on human health and behavior are the most challenging to study. The potential effects on humans are faint. It requires exceptionally large statistical groups and careful analysis to find any signal at all. Observed correlations, which are not direct proof of causation, include small peaks in certain medical diagnoses in the years just after solar maximum, tiny, almost imperceptible rises in basic body measures like temperature, pulse, and blood pressure during periods of changing solar conditions, and even a small, statistically traceable increase in certain mental health diagnoses among people born during periods of higher solar activity. The clear conclusion is that if the solar cycle affects humans, it's in such tiny, subtle ways that only careful statistics can possibly find the signal. It is essential to keep scale in mind. The sun sets the Earth's climate baseline, but the 11-year cycle only adds a gentle tremor on top of the many other powerful climate factors, such as ocean currents and the much stronger influence of greenhouse gases. However, the necessity of precaution remains. Even these small solar changes matter immensely for sensitive technology and high-risk operations like space travel and power grid management. To improve our ability to predict and mitigate these risks, we need to move closer to the source. The primary goal of current missions is to watch cause and effect at the source, where magnetic fields twist, the solar wind forms, and the corona is heated. Better maps and models lead directly to better space weather forecasts, keeping astronauts safe and grids stable. One such endeavor is the Solar Wind Taster. This mission is designed to skim through the inner solar wind, dipping deep into the sun's outer atmosphere to take direct measurements. Its instrumentation is complex. It counts particles, measures their speeds and temperatures, and maps the magnetic field in situ. The scientific goal is to determine if the bursts of solar wind seen near Earth start as slow puffs or fast streams, and to test the crucial hypothesis of whether waves and turbulence are the energy source that heats the corona and drives the solar wind outward. Another critical endeavor is the global viewer. This mission flies in a highly tilted orbit to view regions of the sun that are hard to see from Earth, especially the poles. Its instruments include sophisticated telescopes for imaging the surface, chromosphere, and corona, alongside a coronagraph that blocks the bright solar disk to reveal faint structures. The scientific goal is to link the local solar wind samples gathered by other probes to a global picture, as the poles may hold the most crucial clues to the physics driving the SIM 11-year magnetic flip. Another critical endeavor is the Solar Orbiter, or the Global Viewer. This mission flies in a highly tilted orbit to view regions of the sun that are hard to see from Earth, especially the poles. Its instruments include sophisticated telescopes for imaging the surface, chromosphere, and corona, alongside a coronagraph that blocks the bright solar disk to reveal faint structures. The scientific goal is to link the local solar wind samples gathered by other probes to a global picture, as the poles may hold the most crucial clues to the physics driving the SIM 11-year magnetic flip. To truly understand the sun's magnetic fury, we must touch it. The most ambitious efforts in space science today are the twin missions dedicated to reaching and observing the sun in unprecedented detail, taking us closer than any human-made object has ever been. The first is the Parker Solar Probe, NASA. This mission was officially announced in 2009 and launched powerfully on the 12th of August 2018 aboard a Delta IV Heavy rocket. To fight against the sun's immense gravity, the probe uses a brilliant cosmic trick. It executes a series of 7 Venus gravity assists over approximately 7 years to gradually shrink its orbit. As of late 2024, the probe has executed close approaches as near as only 6.16 million kilometers from the sun's surface, placing it deep inside the corona and solar atmosphere. This is an astonishing feat, 7 times closer than any previous spacecraft, subjecting the probe to extreme conditions. At its closest point, the probe feels a magnetic field and particle flux equivalent to 500 suns experienced at Earth, with temperatures soaring up to 1,400 circ text C, 2,500 circ text F. The probe's survival is a marvel of engineering. It is protected by an 11-centimeter thick carbon composite shield coated with a reflective white surface, a passive thermal defense that must always face the sunday. But distance is not the only challenge. The environment is so dangerous that the probe must operate with a high degree of autonomy. Given the speed of light delay and the frequent communication blackouts caused by solar radio interference, the probe must self-control its sensors, manage data formatting, and archive high-resolution measurements until reliable Earth communication resumes. It is a lonely, self-reliant scientific sentinel at the frontier of our solar system. The second mission is the Solar Orbiter, ESA. Development began in 2012, and it was launched on the 10th of February 2020. Atop an Atlas V rocket. Like Parker, it uses gravity assists from Venus and Earth to adjust its path. It operates on an initial 180-day orbit and reaches its closest approach at approximately 43 million kilometers every 6 months. At this distance, the sunlight intensity is 13 times more intense than on Earth, with temperatures reaching up to 500. Circ text C, 932, circ text F. Its protection is a robust 40-centimeter thick heat shield made with layers of titanium foil, sufficient for its more distant orbit. These missions are complementary in their objectives and unique in their design. They both seek to investigate the corona, solar winds, CMEs, and the magnetic field structure. However, the Parker probe's unique role is to literally enter the corona, where no man-made object has been. It cannot take pictures because cameras simply cannot survive the heat. Instead, it directly samples particles and closely studies the fundamental origins of solar winds and the coronal heating mystery, something impossible to study from a distance. The solar orbiter's unique role is to carry both particle detectors and advanced telescopes, making it the primary source of close-up pictures. Its orbit is also cleverly designed to allow it to track a specific region of the atmosphere for much longer than Earth can, observing the slow buildup of a storm over several days. By working together, the two probes maximize our understanding of the sun, providing both the crucial in situ data and the necessary wide-field imaging. To appreciate the urgency of these modern solar missions, we must reflect on the most consequential space weather event in recorded history. The Carrington event of 1859 remains the single greatest recorded geomagnetic storm, a terrifying yet beautiful glimpse into the sun's true destructive potential. The timeline of chaos began around August 28 and culminated in the main shockwave on the 2nd of September 1859. The sheer scale of this event defines the benchmark for planetary vulnerability. The visual precursors to the storm were astonishing, offering a silent warning of the immense energy gathering on the sun's face. Many massive sunspots appeared, dominating the solar disk. Simultaneously, auroras, the natural light displays usually confined to the poles, were already being seen as far north as Queensland, Australia. The definitive, catastrophic moment occurred on September 1. On that day, two amateur astronomers, Richard Carrington and Richard Hodgson, working independently, both observed and recorded an extremely bright solar flare, a white light flare, visible even against the brilliant solar surface. This visual flash was the precursor to a massive coronal mass ejection that traveled directly toward Earth. Crucially, the speed of this CME was unprecedented. It took only 17.6 hours to reach us, far faster than the typical travel time of several days, which usually ranges from 3 to 5 days. This speed is a critical factor in mitigating future risks. Scientists now hypothesize that a prior CME, possibly from August 29, may have cleared the ambient solar wind plasma between the sun and Earth, creating a literal slipstream or clear path of lower density that allowed the main magnetic storm to race along effortlessly. The global effects that followed were unprecedented, demonstrating the magnetic reach of the sun across vast cosmic distances. The largest recorded geomagnetic storm occurred on September 1859. The auroras, the most beautiful byproduct of this disturbance, were seen globally, reaching far down toward the equator, as far south as the Caribbean, Cuba, Hawaii, and Colombia. This was an unprecedented phenomenon for middle latitudes, proving the extraordinary strength and penetration of the solar magnetic field into Earth's protective magnetosphere. The brightness was surreal. The glow over the Rocky Mountains was so bright, it woke gold miners, and people in the northeastern US could easily read a newspaper outside at night without artificial light. The technological disruption was immediate and dramatic, even in the relatively primitive 1800s. The surge of electrically charged particles interacting with Earth's magnetic field induced massive currents that surged through long conductors. This caused the fledgling telegraph systems across Europe and North America to fail completely. Operators reported physical damage, with telegraph pylons throwing sparks and operators receiving electric shocks from their equipment. The most anomalous and telling operation occurred when some operators realized they could still send and receive messages even with their local power supplies disconnected. The induced solar currents were strong enough to bypass batteries and transformers, powering the system directly. This event was, in effect, comparable to a hemisphere-wide EMP, electromagnetic pulse bomb, harmless to humans, but extremely destructive to the electronics and conductive networks of the time. Geographically, North America and Europe, being the hemispheres facing the sun during the initial strike, were most severely affected by the sudden compression of Earth's magnetic field into the atmosphere. This historic event serves as a stark warning of our planet's susceptibility. Subsequent, though smaller, major storms have occurred, providing more recent cautionary tales of vulnerability in the modern age. A notable example is the event in March 1989, which rendered multiple satellites unusable, jammed radio stations, and caused a massive failure that knocked out power across Quebec for about a day. While this storm caused no permanent damage to large grid components, it confirmed that the threat remains potent and active. The question is not if another Carrington-level event will strike, but when and how unprepared our hyper-connected world truly is. The lessons provided by the 1859 Carrington event are not merely historical footnotes. They are absolutely critical to our existence today, because a modern event of that scale would be immeasurably more disastrous. Our increased vulnerability and near total dependence on technology mean that the complexity of our infrastructure could turn a solar storm into a cascading societal failure. This is no longer a localized outage, but a systemic collapse we must contemplate. The most susceptible technologies are the core veins of modern life: the electricity grid and telecommunications. These systems rely on vast, interconnected networks of long-distance cables and high-voltage transmission lines that act as giant antennas for induced solar currents. When the sun's magnetic field slams into ours, it generates geomagnetically induced currents that surge through these lines. These surges would cause large, expensive transformers to fail spectacularly, not just one or two, but potentially hundreds across an entire continent. This would lead to millions, or even hundreds of millions, being without power for a lengthy period. The resulting situation necessitates long-term repair, as the specialized replacement transformers are not mass-produced but are tailor-made, unique units that can take a year or more to manufacture and install. The sheer scope of this task is a logistics nightmare that would cripple recovery efforts. The estimated economic impact to the US alone is often cited at $2.6 trillion, an event with the power to effectively shatter the global economy and reset our technological progress. The secondary effects of a prolonged blackout would quickly escalate into social chaos. Civilization, as we know it, runs on electricity. Without it, refrigeration would fail across the board, halting the food supply chain within days. Transport systems would cease. Fuel stations require electricity to pump gas, grounding all long-haul trucking and personal travel. Payment systems and banking networks would fail instantly, plunging commerce into paralysis. The internet, television, and radio would be severely disrupted or fail entirely, isolating communities and removing the capacity for coordinated emergency response. Furthermore, most personal electronic devices are battery-powered, and those batteries would quickly run out, leaving the vast majority of the population Without any form of reliable communication, hospitals would struggle, forced to rely solely on diminishing fuel supplies for backup generators, drastically reducing their capacity to provide life-saving care. This bleak scenario forms the basis of catastrophic risk assessment. One non-governmental think tank estimated a recovery time of 4 to 10 years under the worst-case scenario. Their grim analysis suggested the potential for 2/3 of the U.S. population dying within that recovery period from starvation, lack of medical care, disease outbreaks due to sanitation failure, and the ensuing social breakdown and chaos due to the lack of infrastructure and civil authority. This is a chilling but realistic possibility we must contemplate when discussing the seemingly distant, beautiful power of the Sunday. The entire urgency of our current space weather efforts is underscored by the reality of a cosmic near miss that occurred in July 2012. Earth missed a Carrington-sized event by a margin of only 9 days. Had the CME erupted slightly earlier, the direct hit would have served as the ultimate test of our preparedness. This event highlights the core problem: insufficient warning. CME flares are intrinsically fast and unpredictable. Even if we detect the initial flash, the CME can reach Earth in as little as 17 hours, which might not be enough time to alert the entire global population and, more critically, to take essential precautions, such as safely powering down sensitive infrastructure or nuclear reactors. It is therefore not a matter of if a storm of that magnitude will strike again, but when. Understanding the sun's corona, the source of this violence, is vital to better predict these solar storms, giving us precious extra hours, and thus avoiding catastrophic damages to our fragile modern civilization. The entire urgency of our current space weather efforts is underscored by the reality of a cosmic near miss that occurred in July 2012. Earth missed a Carrington-sized event by a margin of only 9 days. Had the CME erupted slightly earlier, the direct hit would have served as the ultimate test of our preparedness. This event highlights the core problem: insufficient warning. CME flares are intrinsically fast and unpredictable. Even if we detect the initial flash, the CME can reach Earth in as little as 17 hours, which might not be enough time to alert the entire global population and, more critically, to take essential precautions, such as safely powering down sensitive infrastructure or nuclear reactors. It is therefore not a matter of if a storm of that magnitude will strike again, but when. Understanding the sun's corona, the source of this violence, is vital to better predict these solar storms, giving us precious extra hours and thus avoiding catastrophic damages to our fragile modern civilization. To resolve the sun's deepest mysteries and fundamentally improve our predictive power, giving us those precious hours of warning against catastrophic storms, 2 pioneering missions are actively redefining our knowledge of the solar system. Their early accomplishments have been nothing short of astonishing and represent a quantum leap in solar physics. The Parker Solar Probe, NASA, is a machine built for records and enduring extremes. It has achieved the closest ever pass to the sun, reaching a remarkable 6.16 million kilometers from the surface as of late 2024. In the process, by executing close gravity assists around Venus, it became the fastest human-made object, clocking in at an incredible 692,000 kilometers per hour. But its true, lasting value lies not in speed, but in its key discoveries. The probe is already helping us build a more fundamental understanding of the magnetic field and corona interaction, informing the solar winds. It has directly sampled and discovered complex solar magnetic fields that sweep through the atmosphere, acting like a cosmic sling to increase solar wind speeds by up to 500,000 kilometers per hour in localized regions. This slingshot acceleration is a crucial clue in solving the puzzle of how the solar wind is propelled to supersonic speeds. Furthermore, the probe found direct evidence of a dust-free zone starting around 35.6 million kilometers from the Sunday. This area is devoid of the fine cosmic dust that pervades the rest of the solar system, a zone believed to be cleared because the intense solar radiation vaporizes the dust particles, literally turning them into gas. This region is a clean, hyper-hot bubble around the star. The Solar Orbiter, ESA, complements Parker's intense particle sampling with its sophisticated high-resolution imaging. It achieved its own milestone by taking the closest ever images of the Sun's surface from a distance of 77 million kilometers. This closer view allows for unprecedented detail, revealing the complex, granular nature of the photosphere. Its most visually striking discovery was the presence of campfires, small, localized explosions on the Sun's surface resulting from disturbances in small magnetic fields. These campfires, while tiny on the massive solar scale, smaller than the massive solar flares, are thought to be the microscopic version of solar flares, possibly providing the continuous, ubiquitous energy needed to superheat the vast corona to millions of degrees. The existence of these constant, small events suggests that the coronal heating problem might not be solved by one massive process, but by the accumulation of countless, minor magnetic pops happening everywhere, all the time. A quiet kind of magic creating immense heat. Future insight from the Solar Orbiter is expected to come from the examination of particles and fields across its elliptical orbit, helping scientists to link these localized surface features, like campfires, to the global space weather environment, and understand the different and localized types of space weather that emerge from various solar regions. The fact that these two missions, each overcoming immense thermal and engineering challenges, are providing such complementary and groundbreaking data, one measuring the plasma and fields in situ and the other providing the crucial high-definition imagery, means that we are closer than ever to decoding the true, profound nature of the magnetic forces that govern our star. We often talk about the sun in terms of light and heat, but the new missions are allowing us to consider its sound. This is a profound, almost poetic way of viewing the star's immense energy output. The simple answer to whether the sun makes noise is that it's silent because sound cannot travel in a vacuum. However, to truly understand the relentless energy output of nuclear fusion, we can use the concept of sound propagation in space. Spacecraft, like the Parker probe, detect not audible sound, but pressure waves and high-energy particles, the physical disturbances that would constitute sound if matter were present. Scientists then take the amplitude and frequencies of these waves, along with the magnetic field fluctuations, and convert them into audible sound reconstructions, allowing us to listen to the sun's environment and the magnetic processes at work. When this energy is reconstructed, the sun produces a constant, deep buzz, a soothing, almost electrical or radioactive-like hum, perfectly appropriate for an ongoing nuclear fusion reactor. The immense power output from nuclear fusion is estimated at a staggering MathBF 3.85 times 1026 watts per second. The calculated volume level this would equate to at Earth's distance is approximately 110 decibels. While survivable for short periods, This constant level of noise would cause widespread deafness and significant auditory damage if we constantly had to deal with it. A fortunate escape for our biology. Near the sun's actual surface, the noise becomes a shattering roar, estimated at 270 decibels. This is a terrifying figure, emphasizing that the math BF 270 dB is 100 million times louder than the theoretical cap in Earth's atmosphere, around 190 decibels. This immense magnetic soundscape is the constant backdrop to all solar activity. As we listen closer, the constant buzzing gives way to a dynamic sound representing the solar wind. Here, we encounter Enigma 1, hyperacceleration. Observations dating back to the 1960 seconds showed that particles originating deep in the corona move relatively slowly at speeds around 145 meters per second, subsonic. Yet, by the time they escape outside the corona, they are moving much faster at over 618 meters per second, supersonic. The profound mystery is the method. Something in the corona is hyperaccelerating the solar wind from subsonic to supersonic speeds in a localized, violent manner. This acceleration happens over a surprisingly short distance, demanding an immense and localized energy source that remains hidden. The Parker probe is specifically designed to sample the region where this dramatic transition from slow flow to supersonic blast occurs. This hyperacceleration is intimately tied to Enigma 2, the coronal heating problem. Based on classical physics, the sun's temperature should gradually drop the further one travels from the core. Yet, the sun's visible surface temperature, the photosphere, is a relatively cool math BF 5500 circ text C. While the thin outer atmosphere, the corona, suddenly jumps to 2 million circ text C. This is a profound paradox. The outer atmosphere is hundreds of times hotter than the surface below it. The required energy transfer is immense. The prime suspects for solving this double enigma, hyperacceleration and superheating, are the chaotic magnetic fields that constantly churn and snap throughout the corona. Listening to the magnetic whistles and chirps the probe detects is the key to finally isolating and identifying the mechanism responsible for injecting this phenomenal, destructive energy. Listening to the sun provides vital magnetic clues that help us decode the two greatest mysteries of the corona: its acceleration and its extreme heat. We first hear the Langmuir waves, sound 3, as the probe crosses the Alfvén's surface, the critical boundary where the corona's magnetic field finally dominates the plasma, freeing it to flow into empty space. These are electrostatic waves formed by tiny oscillations of plasma particles vibrated by light and energetic particle streams racing from the sun through small, organized magnetic funnels. This effect is often described as the magnetic equivalent of a boiling kettle, where the constant flow and sinking of hot and cool material creates sinking zones on the surface that stream out powerful magnetic field lines, scooping up plasma, the fundamental, earliest starting point of the solar wind. Detecting these waves precisely at the Alfvén's surface confirms the point where the sun loses magnetic control over its atmosphere. The sun also produces dispersive waves, which are often reconstructed to sound like high-pitched chirps. These are caused by waves of different speeds spreading out over distance, with faster parts running ahead of slower parts. This phenomenon, known as dispersion, creates small eddies of magnetic and particle noise, where fast waves meet slow waves, manifesting as those distinct chirps. before the system eventually settles into the constant hum heard from Earth. These waves carry energy through the plasma, and understanding their dispersion rate is key to calculating how much energy is being delivered to the solar wind at specific locations. Perhaps the most dramatic auditory insight comes from the Whistler mode waves, sound 4, which form the incessant roar of the Sunday. These are electromagnetic waves that propagate along magnetic field lines, acting as the distant echoes of high-energy events that ring through a celestial body's magnetosphere, similar to the static-like noise heard after a lightning strike on Earth. The contrast is profound. Earth's Whistler waves are sparse, brief clicks. The sun's are a cacophony of wailing wind, with countless individual magnetic moments constantly merging. The implication is crystal clear. Something violent is occurring constantly and widespread throughout the entire corona to generate this incessant magnetic roar. This noise is the background hum of magnetic destruction and energy release. This constant acoustic signature points directly to the leading explanation that could account for both the hyperacceleration of the solar wind and the superheating of the corona, magnetic reconnection, and nanoflares. The term magnetic reconnection is a technically innocent-sounding name for a cataclysmic yet micro-scale event. The theory posits that the sun is a dynamic ball of constantly shifting, powerful magnetic field lines emerging from the surface. When parallel field lines carrying opposing magnetic polarity are forced together and touch, they cannot coexist. They immediately break and violently realign. This magnetic break creates an arc, forcing a massive, instantaneous release of stored magnetic energy and a realignment of the excess field line polarity. The subsequent snap of these field lines further out in the corona is like releasing a stretched rubber band, catapulting immense magnetic energy and plasma off into space. This localized burst of energy is what scientists call a nanoflare. This rapid magnetic force is powerful enough to indirectly heat the surrounding corona to multi-million degrees in mere seconds, solving the energy problem. The immense challenge is that these events are so small and short-lived that they are incredibly difficult to isolate and measure directly. Scientists are not entirely certain that the small campfires seen on the solar orbiter are the precise nanoflares hypothesized, but the scale and constant nature of this phenomenon is necessary to explain the constant solar wind and the superheated corona. The final explanation remains a major unsolved riddle of astrophysics. The ultimate secret to the sun might one day be solved by what we hear, the magnetic whispers and roars detected by the Parker probe, rather than by what we see. Just like listening to the quiet, subtle ticking of a clock allows us to figure out its complex internal function, listening to the sun's magnetic noise is the key to decoding its inner workings. The ongoing data from the probes will determine if the solution is the cumulative effect of these tiny, constant nanoflares, or if an entirely different mechanism is at play. As we contemplate the sun's immense power and its role as a cosmic furnace, we must momentarily bring our thoughts back to our own planet and the massive, growing problem of waste disposal. Earth faces immense, persistent pollution from a disturbing variety of sources. Vast quantities of plastics that contaminate our oceans and ecosystems, lingering industrial waste, dangerous biohazards, and most critically, nuclear byproducts. These long-lived toxic materials pose an existential problem for human longevity and the health of our biosphere. The challenge of nuclear waste is particularly acute. High-level radioactive byproducts, typically from nuclear power generation, remain dangerously lethal for staggering periods of time. Our current solution for the most toxic materials is to bury it deep underground in specialized geological repositories. This is far from ideal. Nuclear waste remains dangerously radioactive for tens of thousands of years, in some cases longer than human civilization has existed. This means we are simply storing a persistent, deadly threat for countless future generations to manage, creating a burden that stretches across deep time. The ethical and logistical demands of safeguarding these materials for so long are a profound challenge that highlights the limitations of purely terrestrial solutions. This overwhelming dilemma often leads to a natural, profound question that arises repeatedly in our community. Why don't we strap dangerous waste to a rocket and blast it into the sun? The immediate, common sense appeal of this solution is powerful. The sun is the perfect cosmic incinerator. It's massive, overwhelmingly hot, and conveniently far away. It seems like the definitive, ultimate answer to our most persistent waste problems. The reality, however, is that the answer is far more complex and involves a profound paradox of orbital mechanics. It's not as straightforward as simply aiming and firing a rocket. In fact, due to the complex physics of our solar system, it's extremely difficult to crash anything into the Sunday. We spend vast amounts of energy launching missions out of Earth's gravity, but falling into the sun is an entirely different and far more demanding physics challenge. The rocket required to send a probe close to the sun, like Parker's solar probe, is one of the most powerful ever built, and even that mission uses complex maneuvers to merely skim the star, not crash into it. This paradoxical difficulty is the single greatest barrier to using the sun as our ultimate fiery waste repository. The intuitive challenge for any space mission is simply overcoming Earth's gravity, which is step one. To break free of our planet's influence, a payload must accelerate to 11.2 kilometers per second, known as escape velocity. This is the speed at which the kinetic energy of the spacecraft is precisely equal to or surpasses Earth's gravitational potential energy. Achieving this velocity alone requires immense power and thrust, but it is, fundamentally, a solved engineering problem, proven repeatedly by every interplanetary mission we have ever launched. The real, overwhelming hurdle lies not in escaping Earth, but in dealing with the sideways problem, the inherent, relentless, orbital motion of our planet. Once a craft is free of Earth's local gravity, it is immediately and relentlessly gravitationally bound to the Sunday, Earth, and everything we launch from it is moving sideways relative to the sun at a colossal speed of 30 kilometers per second, our orbital velocity. We are, in effect, passengers on a very fast, stable merry-go-round. To fall into the sun, this massive sideways motion must be almost completely canceled out. The star's gravity is pulling us inward, but our speed is continually pulling us past the Sunday. Achieving this requires an enormous change in velocity, delta V, the single most expensive factor in rocketry. This brings us to option one, the break and fall method. The mechanism is conceptually simple. A piece of textbook physics. Generate thrust precisely opposite to the sideways orbital motion, effectively decelerating the spacecraft. This deceleration cancels the orbital velocity, stripping the craft of its angular momentum and allowing the sun's powerful, unhindered gravity to pull the craft straight into its center. The required deceleration is a truly staggering delta V of 30 kilometers per second in the opposite direction. This change in velocity alone is nearly 3 times greater than the energy required just to escape Earth in the first place. Herein lies the counterintuitive hurdle of orbital mechanics. It's actually harder to crash into the sun when you're closer to it, because the required orbital velocity is exponentially higher. For example, Mercury, the closest planet, orbits the sun at 48 kilometers per second, which would require an even more challenging deceleration to hit the star. Ironically, from a fuel perspective, it would be more fuel efficient to fly a probe to the outer solar system, where the orbital velocity is lower, decelerate slightly to escape the sun's gravity entirely, and then allow it to free fall from there. This profound paradox demonstrates that falling into the sun is one of the most energetically expensive maneuvers in the entire solar system. This monumental delta V requirement reveals the fatal fuel problem, why option 1 fails spectacularly when confronted with the Tsiolkovsky rocket equation, the fundamental math governing rocketry. To execute this mission, a rocket would need to carry the massive payload, launch the required massive amount of fuel into orbit, fuel the payload, accelerate it past Earth's escape velocity, and then use the remaining fuel to decelerate by 30 kilometers per second. The exponential nature of the Tsiolkovsky equation dictates that the vast majority of the rocket's mass must be fuel needed to move the fuel itself. To illustrate the scale, the mighty Saturn V rocket needed 2 million liters of fuel just to achieve Earth's 11.2 kilometers per second escape velocity for the moon missions. A dedicated sun crash mission would require orders of magnitude more fuel, resulting in a launch vehicle several times the size of Saturn V. Simply put, no modern rocket technology can carry the required amount of fuel to execute this direct, rapid deceleration and survive the initial blastoff, rendering the break and fall method practically impossible for a large payload of waste. This leaves us with option 2, deceleration with gravity assists. The mechanism here is to use repeated planetary flybys to slow the spacecraft down and effectively siphon away its orbital energy. This is a subtle and beautiful application of the three-body problem. The technique involves precisely timing an approach to a planet from behind, swinging the craft in front of the planet and then exiting behind it, effectively bleeding off velocity and angular momentum in a carefully planned sequence. We successfully use this technique for complex outer solar system missions. The drawback, however, is the extreme time commitment and complexity. For instance, the Bepi-Colombo mission, designed to orbit Mercury, a far simpler goal than falling into the sun, required 9 gravity assists and took 7 years just to reach its destination. Crashing into the sun would require complex orbital mechanics and sufficient, repeated deceleration that would realistically take decades to achieve with current technology, making it practically infeasible for the timely disposal of rapidly accumulating, dangerous waste. The complexity and duration of the mission would also significantly increase the risk of an internal failure or a collision with micrometeorites, adding to the unjustifiable hazard of transporting nuclear materials. The orbital mechanics, therefore, are an insurmountable obstacle that forces us to seek solutions here on Earth. Given the immense, almost insurmountable physics problem, the incredible delta V required to negate our orbital momentum, the very idea of using the sun as a cosmic garbage dump fails utterly on practical grounds. It is an engineering nightmare driven by economic folly Firstly, there is the factor of high risk, which borders on the ethically indefensible. Even the most successful and reliable rockets in history, such like the Soyuz series, have a documented 2 to 3% failure rate across all launches. While these odds are acceptable for unmanned scientific probes, the consequence of a failure involving highly radioactive nuclear waste or dangerous biohazards would be catastrophic beyond imagination. A launch failure or mid-flight explosion would not result in localized contamination. It would create a wide-ranging, devastating plume of radioactive material or infectious agents scattered across the atmosphere, resulting in the worst possible outcome: widespread environmental contamination of the atmosphere, oceans, and populated land masses. The long-term cleanup and health costs associated with such a global disaster would dwarf the cost of the mission itself. It is a calculated risk that simply cannot be justified by any nation that values its population and environment. The potential for irreversible global harm makes this idea a non-starter from a planetary security perspective. Secondly, there is the unjustifiable cost, which quickly escalates the project from merely expensive to financially absurd. As we established, the scale of the rocket required to execute the necessary 30 kilometers per second deceleration would be enormous, a vehicle multiple times larger than anything currently in service. The cost of designing, building, testing, and fueling a rocket capable of this super heavy lift and extreme deceleration would place the project in the tens or even hundreds of billions of dollars. No sane national or international budget would ever approve a project that is guaranteed to be insanely expensive for the sole purpose of disposal. The opportunity cost is too great to ignore. The budget required for this ultimate garbage mission would be far, far better spent on other missions that genuinely advance science and humanity, such as building orbital telescopes, funding climate research, or developing the solar probes we discussed earlier. Spending such a colossal sum simply to avoid solving a terrestrial problem is an economic and scientific waste of resources. Finally, for the theoretical necessity of space disposal, there are cheaper alternatives that circumvent the entire sun collision problem. If the goal were merely to get garbage far away from Earth, it would be far easier, quicker, and cheaper to shoot the garbage out of the solar system toward interstellar space. The required acceleration needed to achieve the solar system's escape velocity from Earth's orbital speed is only 12.1 kilometers per second. This flyaway mission is technically and financially feasible with current rocket technology. By placing the waste on a hyperbolic trajectory out of the solar system, we ensure the material will never return to threaten Earth. This strategy achieves the objective of permanent disposal without incurring the extreme delta-V penalty and the high risk associated with launching a huge, deceleration-capable rocket. The final conclusion is clear. We don't shoot garbage into the sun because it's super hard, super risky, and super expensive. The engineering challenges are a profound paradox of orbital mechanics. It's easier to leave the solar system entirely than to fall into the sunday. The true answer to our pollution problem must be a realization that we need to be more conscious about consumption, recycling, and developing safer, long-term storage solutions here on Earth, rather than relying on an impossibly distant, high-risk, stellar solution. The sun may be our ultimate power source, but it will never be our cosmic landfill. And so, our journey ends where it began, but with a profoundly deeper understanding of the star that effortlessly governs our existence. We have spent this time together tracing the immense arc of the sun's life and the incredible complexity of its inner workings. We return, finally, to the quiet hill and the sunrise. Before this exploration, that sunrise was simply a given, a reliable splash of light and warmth. Now, we see it as a scientific marvel and a cosmological achievement. We have traveled through the magnetic fury of the sun's atmosphere, down to the unimaginable pressure of its core, and out to the edge of the solar system, discovering that our star is not a calm lamp, but a chaotic, powerful engine that dictates space weather and holds the power of utter catastrophe. We hope you now truly profoundly appreciate the incredible voyage of the photons that warm your skin. Recall the journey. It began with the immense cosmic cloud collapse that birthed the star, where gravity overcame gas pressure. It continued in the plasma melting pot of the core, where the laws of quantum mechanics alone, the strange loophole of quantum tunneling, made fusion possible, transforming mass into energy. This newborn energy then embarked on its hundreds of thousands of years of struggle through the dense radiative zone, where it was absorbed and scattered countless times, making that agonizingly slow, random walk to freedom. Only then, after an epic journey across time and density, did it make the final, rapid dash to our planet. The warmth you feel is not just heat, it is the physical culmination of deep space physics, a triumph of gravity and electromagnetism. It is a daily miracle, delivered to us effortlessly every morning, but achieved through constant, hidden cosmic struggle. Our exploration has revealed that the stability of the sun is a profound paradox. We marveled at the hydrostatic equilibrium, the perfect balance between gravity pulling inward and fusion pushing outward, that allows the sun to burn steadily for billions of years. But we also uncovered the chaotic systems riding on top of that stability, the 11-year solar cycle that drives magnetic storms, and the coronal heating problem, where the magnetic fields superheat the sun's atmosphere to millions of degrees. These are not just academic mysteries. They are the keys to predicting and mitigating the greatest space risk we face. We spoke of the Carrington event, a stark reminder from 1859 of the sun's power to cripple technology. That event, which fried telegraph wires, would translate today into a multi-trillion-dollar catastrophe that could plunge millions into darkness for years. We learn that the urgency is real, underscored by the near miss of the 2012 CME. This is why the Parker Solar Probe and Solar Orbiter are racing toward the sun, risking destruction to bring us the data necessary to improve our warning time from hours to days. Every magnetic whistle and every particle measured by those probes is a piece of the space weather puzzle. And finally, we put the sun's power into perspective with the paradox of disposal. We saw that crashing a rocket into the sun, the seemingly simple solution for our nuclear waste, is actually one of the most difficult and expensive maneuvers in all of orbital mechanics, requiring an impossible amount of fuel. The physics tells us that the sun is not a cosmic landfill. Our true solution lies in better stewardship here on Earth. The narrative of the sun is far from complete. There is still so much more to uncover about its future transformations and profound impacts. The journey is ongoing, and the mysteries remain captivating. We still have to fully decode the magnetic dynamo that sets the 11-year rhythm. We have yet to definitively prove the role of nanoflares in heating the corona. And far in the future, the sun will undergo its final, dramatic transformation into a red giant, a cosmic fate that gives us a sense of the immense scale of geological and stellar time. This exploration has equipped you not just with facts, but with a contemplative awareness of the scientific forces that govern your world. We invite you to continue your journey of exploration with us, asking the big questions and seeking the scientific truth. Every sunrise is a chance to marvel at the daily miracle provided by that magnetic, magnificent star.